Hello, welcome to what would have been our second meeting of CRIM 5900, Descriptive and Inferential Statistics. So today we'll be talking about organizing and presenting empirical data, and importantly, this will be our introduction to the R statistical computing environment. So it'd be better to do this class in person, but having this as a recorded lecture can be beneficial. It can be a video you can come back to. I'm going to provide plenty of resources for you to use to get caught up. And in our next class meeting, I'll make sure that we are all pretty comfortable with doing what we need to do up to this point in the software, which will be fairly rudimentary, just starting off easy. So there's a few things that we should do to get set up. So first, you will find I will email you, and I also upload a link to Blackboard in the week 2 lecture materials with a video on how to install R on your RStudio on your own computer. It's something that I recorded for an undergraduate class back in the spring, but that kind of stuff doesn't change. So you can go ahead and check that out if you want to install it on your own computer. It will also be possible to use R and RStudio exclusively on the computer lab computers, but really, you should be trying to get some of this work done at home. So I would strongly encourage you to look into installing these on your own computers so you can do that work. So first, as a little bit of setup here to get started, here I am on the Blackboard main page for the website of our class. If you go down to data sets, you will see a list of data sets here. The data set that we will be using for our practice here today is this Attitudes on Crime and CJ. This is a subset of the General Social Survey, which is a nationally representative survey of US adults. They ask them hundreds of questions on lots of different things, but they do ask a fair number of questions on criminal justice related issues. So I've cleaned up those data and made them available as an SPSS file. Now, the reason it's an SPSS file is that that's a very convenient file storage format. So I do use that format for storing a lot of files, but we're not going to use SPSS. We're going to open that file in R. So what you need to do is you need to download this file to your computer. Listen to me. You need to download the file to your computer. We are not opening it yet. You're downloading it. So what that means is that if you are on a Windows machine, you should be able just to click it, and it will download here. Now, again, what you want to avoid is any kind of situation where the computer's saying, what program do you want to use to open these data? We're not opening anything. We are not opening the data. Just trust me. I apologize if I'm raising my voice, but this is something that comes up every semester, and I just need to be abundantly clear. We're not opening anything. We are downloading the data. So I'm on Microsoft Edge. It just downloads when I click it. Chrome or Firefox might be different, depending on what you use. If you are on a Mac, you would need to do a 2-finger click on the link, and you will get an option that says download linked file. Okay, so download this file to your computer. Don't open it. Download it to your computer and find where it got downloaded to. So for me, this went to my downloads folder, and from there I could move it to someplace that makes sense. But I also know that this is in my my folder. I already have these data because I made it for this class. All right, so just basically get these data, download them to a folder. Under no circumstances are you choosing a program to open these data. So if your question to me, is something like, my computer doesn't have a program that can open these data, take a step back. We are downloading the data to the computer, not opening it. Okay. Got that out of the way. So you need to get those into a folder somewhere. Great. So let's get started. So just a little bit of background here. make sure that we're on the same page, understand kind of what we're working through here. What we're going to talk about in class today in the context of working through this software is understanding what we mean by data and data structures, working statistical software into the analysis of data, and then displaying distributions of data both in tabular or table formats and visually using graphics and figures. So as a super general definition, when I'm talking about data, I'm talking about what we get on the other end of our measurement process. So, we have a specific research objective. In an explanatory process, we are interested in looking at how certain variables are associated with one another. So what we do is we have maybe these particular concepts, these particular constructs. We have devised ways of measuring them. Let's say we distribute a survey, we create questions, we send the survey out, or we come up with some definition and we comb official record data for that stuff. But what we ultimately end up with at the other end of our measurements are the actual things that we collected data on, collected our measurements on. Those are our data, all right? This is the empirical information that we're going to use to address our research objectives. Now, you could think of just about any data set as being a matrix array of some form. By a matrix, I mean a spreadsheet. We have rows, we have columns. These are meaningfully organized to represent certain things. So in what we'll call a tidy data format, every row is a unique unit. So if we distributed surveys to some sample, right, then every row would be a survey respondent. Okay. If we were collecting information from law enforcement agencies, based on administrative statistics like what you would get from uniform crime reports, for instance, every row would be a police department. So every row is a unit. Units of analysis will vary, from each data set to another. There are some commonalities, but for us today, we're going to be looking at a data set that's a survey responses. So every row will be a unique person. Now, there are other ways that we could organize this. So if you have any kind of longitudinal data, those are most often organized, analyzed what's called a long format, meaning that every row is a unit observed in a particular time point. And so that gets a little bit more complicated. We'll cover that next semester in regression analysis. But for right now, every row is a unit. Now, every column of this matrix is a variable. And these variables represent different characteristics of our units that we have measured and are interested in examining variation in. So we might have a variable for our survey respondents that represents a unique respondent ID. That's not something we're really interested in analyzing. It's just used for administrative purposes. But then we might have something like, do they support the death penalty? Is the survey respondent identifying as male or female? What is the respondent's age and years, et cetera, et cetera. So these would all be represented in different columns of this matrix. Now, at the intersection of every row and every column, there is a specific observation of a specific unit. And so we refer to these as cells. And so in any given data matrix, you would have individual cells. In any given table where we're presenting information, you can have cells. But what's important here is that cells can be subscripted using, this is what's called kind of matrix notation here, that it's one number, comma, and then another number. These represent the row and the column. And so right here, notice that unit 1, so we have row 1, so we have cell 1-1, cell 1-2, cell 1-3. It's row 1, column 1, row 1, column 2, row 1, column 3. Down here, we have row 4, column 1, row 4, column 2, row 4, column 3. We can eventually we can use this in R for identifying specific subsets of units, either by their location in a matrix or by their attributes, which will be a little bit more useful. We'll kind of cover that next week. But in any case, it's important just to recognize that these intersections of rows and columns are unique observations of given units, right? So ultimately, like a lot goes into the research process. It does, if you're starting from scratch, it can take a long time to get the eventual results of your measurements into a form like this. Luckily, we have some available data from the General Social Survey, so we are going to jump right into it in terms of let's get this type of data format into R so that we can work with it. Okay, so up to this point, should have taken these data, and go ahead and pause this or whatever if you haven't, but you are downloading these data to a folder, and you know where that folder is on your computer, right? So like I would recommend making a folder for this class, or if you already have a folder for this class, make a folder called data or something like that within that folder so that it's clear where you're storing this stuff. So we're going to have a few things that we're going to work with here to get started, just so you know everything that's at our disposal. So I'm going to go down to lecture materials. I'm going to go to organizing and presenting empirical data. And so there's a few things here. So first of all, the slides that I'm sort of presenting off of are here, if you want those. What I'll be talking through in R is this guide right here, which is a PDF guide that shows basically all of the R code that I'll be writing and describes what they do. And this is essentially what I'll be walking through. So you can kind of go back to this, run the script yourselves, type it out, see that this is a template to work off of. But this is a kind of a nice tutorial that I've put together. At the same time, there is an R script. And again, we're going to be writing out this R script, but there is a script that is already made that will reproduce all of this analysis and kind of data manipulation. This is a resource for you where if you are typing something out and it's just not working, you can come back to this document. You can see that this is just the R code, from that written tutorial, but we'll cover, how to open those things up here in a minute. So don't mind my email. Okay, let's get rolling here. So if you haven't already, you should look into installing R or getting onto the university VLabs, and you can open up R and RStudio there. But if you do open up R, this is what it looks like. So what is R? R is it's a statistical computing platform. You can think of it as something like SPSS, Excel, SAS or Stata, any one of these other programs that its purpose, is for, reading in data, working with those data files and performing analyses, of those data files. What makes R different from these other platforms, like in particular, SPSS is kind of a good foil here, is that R is a dedicated statistical programming language. So it is entirely script-based. It is not, there's no drop-down menus, where if you've worked previously in SPSS, you would know it's like, okay, well, if I want to get, a frequency distribution, we go to analyze descriptive statistics, frequencies, you get a menu, you check off certain boxes, you'll drop in variables and click OK, and then something will pop up. And that's fine. That's very user-friendly. That's what I use in like the online versions of this class, because it is it's easier, to work with, and it's really all that's necessary, for this class. But for us, those of us who are kind of gearing up to do this sort of thing for a living, right now, R is the tool, for statistical computing for a bunch of different reasons. Now, I'll get into some of this, but part of it is that it is free. It's an open source language. That means that you do not have to pay money, in order to work with it. There are certain things that you can pay for on top of it, for support, and that's in particular through RStudio. But we're not going to concern ourselves with that, for right now. We just need to use the free version here. It has a very active community of scholars and researchers, computer scientists and statisticians who are actively developing cutting edge techniques to implement in R. Now, some of these are extremely sophisticated analyses. Some of these are just tools that make your life very easy. So, just as a little context, all the way through halfway through my undergrad through halfway through my PhD program, I used SPSS exclusively. A little bit of Stata here and there, but I used SPSS exclusively. And SPSS is well known for being kind of the best in class tool for data management and manipulation. And I eventually started running into very simple problems that I needed to solve, very relatively simple techniques that I needed to apply to my data that SPSS could not do. And part of the reason for that is that it was a proprietary, platform. It's owned by IBM. For SPSS to do what it does, IBM needs to have its developers, put that code in, re-release the program. You buy it again for I don't know. It's usually a couple $100 for an individual to buy it. It's a bit behind the curve because it takes them a while to develop those things. And they'll only put out a new version if they think they can make money off of it. That really puts them, into the firmly in the shoes of the blockbuster video, of statistical computing. It's a bit behind the curve in terms of how quickly stuff is developing. So I started using R because I needed it. I needed some of the capabilities that it had, and it is, at least in the right hands, but a extremely powerful software for data manipulation. So it takes tasks that used to take me literally days in SPSS. I can do them in a matter of minutes. Eventually that could be very useful for some of you. For others, just having this bit of programming experience is an awesome addition, to your resume. So like having SPSS on there is good. It's kind of a given that somebody in an applied social science program, whether master's or PhD, would have a little bit of experience, with SPSS. That's fine, but it's not going to make the same impression as having experience with R on your resume. So there's a lot of different reasons that we use it. But so R is a very bare bones environment. So like here, if you just have base R open, you basically have this console screen. We're not going to work off of this. We're not going to work with base R. You need to have this installed, but we are going to be using RStudio, which is, if anybody plays, online games like I do, this is basically an interface upgrade for R. It's a new UI tool, for it, where it is the same language, it has many of the same capabilities, and then some, but it's designed to be more user-friendly. So we'll kind of talk through the shape of R, and the different screens that we're looking at here. But what we are gearing up towards is, so understanding how R works, understanding how scripts work, opening up our data, and then working with those data. So that's what we're going to get going on here. So first of all, when we think about what R can do, it is kind of at its base a big calculator. So like here in the console, notice that I have this blinking cursor, down here. I could do something like 6 plus 7, and hit enter, and it will return something for me, 13. So we could ask R to do a lot of stuff just by typing stuff out into the console. The problem here is that that is not reproducible. If like in SPSS, if you're working through drop-down menus, you perform an analysis, you open it up, you go through the menus, you ask for your stuff, you get the output. If you screwed something up, you need to go do it again, or you need to stop and come back and then do it again, you would literally do all that again. You type everything back out, go through the menus, do all that. It would be better to work off of script, which is like syntax, in SPSS. So what we're going to do, with any time that we're working with R, is we're going to work off of a script window. So what I want you to do is go up to File, New File, R Script, and click that. Alternatively, there's a little white sheet right here with a plus sign. If you click that and just click, so this is New File, and just choose R Script, which is the top option here. And what you will get is a window that appears up here. You can reorganize these panes eventually, and I'll describe what these other ones do soon, but this is our script pane. So this is where we are going to enter commands and then run them off of this. In a script pane, like you can consider this as kind of the record, of the work that you're doing. So there'll be times when we are writing out commands for R to run, and sometimes we are writing notes to ourselves in it. So first, what we should do is indicate what this script is for. So to make a note, you can put a hashtag, and notice that it turns green. When you do that, that means it's a comment. We can't change the color scheme here, but if you're on the default color scheme like me right now, then green is a comment. So we put a hashtag there. If you put a couple of them, that can just be like a heading system, for instance. So here I'm just going to write, CRIM 5900 intro to our script. Okay. And then it's probably a good idea, write your name, write the date, whatever. So something just to indicate if you open up this file again, oh yeah, I remember what this is, what I was doing here. So for any given script that we start writing, it's going to have a few different starting components in it. Now I'm going to call this starting section setting up our workspace. All right, so just follow along with me for right now. I'm going to do 4 hashtags and write, set up workspace. And I'll do another 4 hashtags. And when you do that, when you put at least 4 on either side of a comment that you do, if you go over here to this little button, it looks like a little table of contents. This is your document outline. You are creating subheadings, so you can eventually skip the certain sections in your code. This can be, it's not that useful when your code is very short, but for certain manuscripts that I've written, my script is thousands of lines long. And it has dozens of different sections to them. So we have to have a way to navigate those. So set up workspace. So there's a few things that we'll do when we set up our workspace. So one of these will be installing packages. So when you download R, it can do some a lot of stuff, some basic things, some advanced things. But the real strength of R comes from these pieces of software called packages. Now, packages are written by people. They're written by applied researchers, statisticians, computer scientists, et cetera. And they are collections of either data, functions, and things that are meant to be powerful and make your life easier. They do certain things. So for instance, one package is designed for reading foreign data files into R, so various different types of data into R, and that's called Haven. So to install that package on your computer, we're going to write out a function and then ask it to install that package. So the function to install packages is incidentally install.packages. So install.packages and then open close parenthesis. So anything that comes before an open close parenthesis is a function in R. So install packages is for opening packages. So then in quotes inside the parenthesis, I'm going to write Haven, all lowercase. So what this does is when I run this, it will install the Haven package. Now, if I want to run this line of code, what I can do is highlight it and then click run. I could put my cursor on that line and just click run, or highlight it or put your cursor in the line and do Control Enter if you're on a Windows machine, or Command Return if you are on a Mac. So highlight, run. And once I do that for my script, it will now come down to the console. And so it's working. See, this little stop sign means that R is currently working. Yours might look a little bit different than mine because I already have Haven installed. So your output might be a little bit more complicated than mine at this point, but this is good. So live, package Haven successfully installed. We don't really care about this other stuff down here. We just care that we did not get a message that says warning or a message that says error. So I'll cover those two things later as we come to them. So right here, no news is good news. Now note that when you install a package, you only need to do that once. The package is now on your computer, but what you would need to do every time you boot up R is you would need to load that package into your computer's memory. And so really at the start of any script, we'll install packages that we don't have, and we will load the packages that we will need for that analysis. So there's not a tremendous number of packages that we're going to need in this class. We are going to need Haven. There's one more that we're going to use quite a bit. It's a big collection of packages called Tidyverse. So we should probably install that too. So install packages, Tidyverse. So Tidyverse is a collection of a bunch of different packages that are written by all the developers at RStudio. They're designed for statistical graphics, for working with data, lots of very useful tools. So it's a very useful package to have. I will also install that right there. I just did the command control enter. I mean, so you didn't see me click run, but that's how I got it to run. Warning, your computer might be working for a few minutes here as it installs stuff. Tidyverse is very big. It has lots of different components to it. So I already have it installed. So my output here is very simple. But do not be alarmed if yours is running. If it's running for like a super long time, like let's say like 5 minutes plus, I don't know what's happening with that. Maybe send me a message about that, and we'll see what we can do. But sometimes you just need to be a little patient as it does these things. But again, you only need to install once. Okay. So once we have packages installed, we will need to load them. Now, to load a package, we use the library function. So library, open close parenthesis. And if you are on RStudio, once you put your cursor inside the parentheses, it will produce a drop-down menu of all the different packages you have installed. Now, I use R for a living, so I probably have a ton more packages than you do at this point. But we can always, start typing in, and it will start to narrow down based on what we have. So what we want to do is we want to import the Haven package, so library Haven, and run that. And then we want to, and right here, I said to run that, and it showed up down here in the console, down here, and no news is good news. Like if it didn't work, like let's say I did not have the Haven package installed, I would get an error message. And an error means R is telling you, I tried to do what you wanted, but I couldn't, for some reason. Usually the error messages are a little tough to discern, but like right here, for instance, note that R is, and note Haven, in this function here, Haven is not in quotes. So library does not need it in quotes, install packages does. This is just a little idiosyncrasy with the language. It will eventually figure out when stuff needs to be quoted and when it doesn't. But it's very specific. If I did Haven with a capital H and then ran that, it would say error, there is no package Haven. So again, it's very specific. So it's Haven with lowercase h. So I will library in that, and I will library in Tidyverse and have it do that as well. This will take a little bit longer because it is a big collection of packages. And so these are all the different packages it loaded. We'll talk about conflicts later. These are not a problem. So this is good. This is what you want yours to look like, if it works. So once we've done that, again, you only need to install packages once. You need to load the packages every time you turn on R and work with a specific script. So what I would actually do here is I would put a comment in front of each of these so they won't run again. Like we don't want to continually reinstall packages. Just put a comment in, and now if I ran these lines, they're just comments. R does not think that they're functions it needs to work with, so that's good. So like do that for lines you don't need anymore. But what we'll do now is I'm going to save this. I want to save this file so that I can come back to it and open it later and continue working if I want to. So you could click this defunct piece of technology here, this floppy disk, to save it, and it will ask you to save it somewhere. So I'm going to go to the folder where I actually have my data in. In-person version, lecture materials, week 2. I'm actually going to save over this other script. So it's Jason's CRIM 5900 R1 script. So you might need to just, you'll have to save a new file because presumably you don't have one already there to overwrite. But we are saving this script file, and now if we close R and reopen it, we can open up this script and continue working. Okay. So what we've essentially done here already is we've started setting up a script for working with our data where we are loading in the capabilities that we will need by installing specific packages. So Haven for reading in foreign data, Tidyverse for working with data. And now we'll go on to the next step of setting up our workspace, which is setting the working directory. Now, the working directory is the folder that you are working out of. What this is we want to tell R the folder where our data are. There are a couple reasons that we do this. Like, there will be times that we ask R to do things like, hey, create a graphic and save it. And it wants to know, where should I save it? If we say, open these data, it says, where can I find those data? So by setting the working directory, we are answering those questions ahead of time. So to do this, go up to this menu up here, Session, and scroll down to Set Working Directory. We have a few options here. If you choose to source file location, that is whatever folder the script file is in. So that might be the folder with your data. It might not. What I would recommend is you click Choose Directory. When you do that, you'll get a File Explorer window. And what you want to do is find the folder where you saved the attitudes on crime and CJ data. So for me, teaching, descriptive inferential statistics, well, I keep doing this. In-person version, lecture materials, week 2. Now, when you come in here, you are not going to see the data file, right? That's because we are not opening any data yet. We are only telling R where the data can be found. And this is why you need to know where your data are. So if your data are in your downloads folder, you can go ahead and select that. I wouldn't recommend working out of downloads, but look, if that's where the data are and you're uncomfortable moving them, go ahead. But for me, I know that they are in this folder. So once you click that, this pane down here, this does a lot of different things. This is your graphics and your files pane. It will show files in your folder. Now right here, I can see my data file right here, attitudes on crime and CJ, right in that folder. Now note that in your console, after you chose that folder, something ran down here, the setwd function. So what I'm going to do is I'm going to copy that. So copy, and then I'm going to paste it into my script. It goes off screen a little bit. That's fine. If you have a really long file path like I do, that's fine. But now, like the next time that we open up this file to work on this particular project, we don't need to do session, choose, set working directory, choose directory, navigate to the folder. We can just run this line and it will set that working directory. But what you want to be able to see is your data, the attitudes in crime and CJ in this folder. Right. So let's start working towards data here. So just trying to be consistent with the guide I have. Just setting a heading. So again, I'm going to do 4 hashtags on either side, and that gives us 2 sections. I'm setting up the working directory and then getting started with R commands and objects. So like I mentioned before, R is basically a big calculator. Like we can ask it to do stuff, 5 + 5. And note here, the spaces on this don't matter. I could just do 5 + 5 like this and run that, and it will give me 10. I like to put spaces in when I can because it's cleaner. Okay, so again, 5 + 5, 10. Those both work. And I run this off the script, and I have this record, of the work that I did, up here. But this isn't really unlocking the strength of R as a language. So here, save to an object. Let's try this. If I did x equals 5 plus 5. Let's go ahead and run that. And what you'll see is it runs. We don't see 10 down here like it printed before. Instead, up here in our environment, we see we have this thing, x and then 10. This is what we've done is we have created an object called x, and we've given it the attributes of whatever's on the other side of the equal sign. So we've given x the properties of the number 10. So what could we do with this? We do x divided by 5, and it gives us 2. We could do x times 100, and it gives us 1,000. So like we can save things to objects and then work with objects. Object names are totally arbitrary. So I could make, a new object called JSON, equals the, square root of 4. So the square root function will give you the square root of whatever number you give it. And it returns, the object JSON, which has the value 2. So then I could do, JSON plus 1. Okay, 3. So we can, create objects that have any name. We could give them properties. But the basic idea is that we can save stuff to objects and then work with those objects. Now, the way that we can read these lines here is we read this as JSON gets the square root of 4. Gets whatever's on the other side of this command here. Another way of writing this that is equivalent. So like right here, if I said x equals 4 plus 4, and then x, less than symbol minus sign. So I make an arrow, pointing at 4, or pointing at x and do 4 plus 4. These are both equivalent here. So the equal sign and then the arrow. Some people like the arrow because it is more explicit. It's more explicit that whatever's on this side is going into x. So x gets whatever's on this. For me, I use the equal sign because it is fewer keystrokes, and I'm a very lazy person. Okay, there we go. So each of these are equivalent. Now, note, when I just did this, I had this object before, x was 5 plus 5, so it had 10. I just made this new object x, and it now has the value 8. So I didn't get any warning that's like, hey, careful, you're going to overwrite your object. It is not a big deal because I can, if I wanted that original one back, just go back up and run that line. And now I've got that. But also note that, like I mentioned with the Haven package earlier, R is case sensitive. So if I said, x minus 2, capital X, I mean, error, object capital X not found. So it is specific, in terms of will get error. Oh my goodness, I can't type, as you can tell. Will get error. So it's very specific, in terms of the object names. If you call it lowercase x, or you call it JSON with all lowercase letters, that is the name of the object, literally. So now that we understand sort of, how objects work, let's talk about reading in data. My goodness, this is a rough morning. Okay, so in order to read a data file into R, we're going to save it to an object, that is in our environment up here. So before we get started with that, I'm actually going to clean up my environment up here. So the clean up. So the function RM stands for remove, and it will remove objects that you name. So if I did JSON, comma, X, and then run that, it deletes those 2 objects. Again, if I wanted those objects back, I would just run that code above. But now those are gone, from my computer's memory. Now, again, you might not have created an object called JSON. I created an object that had your name in it. You would have to name it that and tell it, otherwise it'll say error, remove, didn't find JSON. You write in what you have there. If you just have X, just do remove X. So anyways, what we need to do to read in a file is we need to save it to an object, and we need to use a function that will read the file in to do that. So here, what we want to do first is designate an object that what we want to call our data file. So we are going to be working with data from the General Social Survey. So I'll call my object GSS. I like to use very short names for objects, usually something that's 3 characters or fewer. Very often I'll call my data just D, for data. But here I'll call it GSS. What we want to do is GSS, and just follow along with me for right now in terms of how we are working through this, because you have to take a little bit of my word for it. So we're going to do GSS equals read underscore SAV. Now, why are we writing that? It's because the attitudes on crime and CJ is a .sav file. So we need to use a function for reading that type of file. If it was a CSV file, we would do read underscore CSV. If it was a stata file, we would do read underscore DTA. So we would have other types of functions for reading in specific files. But here it's a SPSS file, so we will use read underscore SAV. And now what this wants is, in quotes, the exact name of the file. And so as long as your working directory is set, and you can see your thing here, all you need to write in is the name of the file. Otherwise, if you haven't set your working directory, you would need to write in the entire file path. So like C:// program files / person / stats / data / nobody wants to write all that stuff. Do the set working directory and find that folder with the data. So here I'm going to write in literally attitudes. This is going to be really hard for me today. Attitudes on crime and CJ .sav. Now note, if that, this is what my file is named, literally attitudes on crime and CJ .sav. If you, sometimes I find when people on Macs save something, it gives them weird names. Like it gives them a name like squiggly line, attitudes on crime and CJ. Or if you've downloaded it multiple times by accident, you will have like attitudes on crime and CJ 1 or something like that. Whatever this says, that is the name of the file. Okay. So once we do that, we can test and see if this works. So I'm going to run this. Now, if it succeeds, you will now see that there is an object up here. So it's GSS, has 1,321 observations of 23 variables. Okay, like these are our data. If you get this, this means it worked. If you, let me just, as an example, I'm going to put a space in here. It's not the name of the file. You would get an error, data not found. So there's lots of reasons why your data wouldn't be found. You either are not naming it correctly here, or you have not set the working directory. Those are 2 very common reasons. One thing that can help a little bit is, I'm just going to delete this for a second, is once you're in the brackets here, if you hit tab, it should, or maybe if it's in quotes, hold on. I just put quotes. Okay, so put in quotes and then hit tab, and it will pull down a drop-down menu of all the files in your working directory. So I could just click, attitudes on crime and CJ there. So once you've confirmed that you can do this and it opens the data, you're going to do one more thing. You just have to take my word for this, that we need to do this for right now. Is after that, I'm going to write %, greater than symbol, %. So basically it's pointing in this direction. This is an operator called a pipe in R. It's a way of basically saying, take this, then do something else. We're going to write as underscore factor, open close parenthesis. Okay, and just go ahead and run that. And you should have your data still up here. just to preview what that does is, if anybody who's worked with SPSS previously would know that SPSS, when it encodes categorical variables, it actually encodes them as numbers. Let's say you have a variable for gender, has values of male and female. In SPSS, it's actually values of, typically it's like 1 and 2. And it will say, yeah, 1 is female and 2 is male. And then you would have to tell SPSS to do special things to treat it like a categorical variable as opposed to treating it like a numeric variable. So if we did not do this part and you just read in the data, what R would say is that, yeah, you have a variable called gender, in there, and it has values of 1 and 2. But it would not apply those labels to them. It would still treat it like a numeric variable. But if we write as_factor here, what this is doing is it's saying if any variable has value labels, apply those labels to those different values and then just convert that into a categorical variable. Thank you very much, is what that does. So we'll talk more about that later once we talk about different variable types. But let's take a look and see, did this work? So if you want to take a look at your data, you could click this down button right here. It will produce this kind of drop-down list we can look through. We see a bunch of different variables here. We have the respondent ID. We have the year that they responded to the survey. So fear of crime, values of no and yes. And so descriptions of these data are in the analysis project. This is one of the analysis project data sets. We'll talk more about this later. Another way we can take a look at this is if you just click on the name of the object here, you notice it runs this view function. And now we can see this spreadsheet here. We can scroll through, and what you should see, are values. So fear of crime, yes, no. Not enough to stop crime, yes, no. Symbolic ideology, fancy way of saying political ideology, liberal, conservative, etc. If all you see are numbers here, then you need to do this as, pipe as_factor part, okay? But we will, so go ahead and do that if you haven't already. But once your data look like this, then we are in the right boat. Okay, so we've got our data into R. Now, any object in R has a class. A class defines like what is this object, and so we can just check, what the class of this object here is. So class GSS with the class function. And it actually has a couple different ones here. So these TBLs you can read as Tibble. And so the important one here, though, is data frame. So R calls data matrices data frames. And so a data frame is a matrix that has units, has rows, has columns. Variables are in the columns, units are in the rows. Okay, so this is what we want. We want it to be a data frame. This particular data frame has 1,321 rows and 23 columns. So let's look at working. So working with data frame variables. So let's say that we wanted to check out one of these variables in the data. So note that, if we take a look here, we might see the variable, oh, okay, support death penalty is one that we'll look at quite a bit here today. I want to check out this variable. Let's see what it is. So, a function that we'll see for producing frequency distributions is the table function. So if we write table, open close parentheses, and then support death penalty, okay, as support_death penalty. There are no spaces in variable names. It will say error, object support death penalty not found. Now, the reason for this is that this column here, support death penalty, is a column of this GSS object. So in order to reflect that, what we need to write is GSS $ support death penalty. That's the name, of this variable here. But what this is saying is take the data frame GSS. Then I want the specific column, so, numerated by the $ here, support death penalty. If I run that, it tells me I've got 458 no's, 863 yeses here. Okay, now we're working with something. let's do something to another variable. So as we'll see later, if we want to get the mean, the arithmetic mean of a variable, we could do so mean GSS $sign. If you're in RStudio, you get this drop-down menu. Let's scroll down here and check out age. So how old is the average respondent? In these data, we'll see that the average respondent is 47. It's an all-adult sample, so there's no extreme values in the low end to pull the mean down. So it's going to be a little bit higher on average. So you have that. There are other functions that we can run to do certain things. So, table, as we'll see later, is for frequency distribution. The mean is for calculating the mean. Okay, but like as we'll see, if you want a percentage, there's another function for that. If you want a standard deviation, there's another function for that, et cetera, et cetera. A very helpful function that we'll want to use is the summary function. So summary does a lot of different things depending on the type of data that you give it. And we'll talk about that here. We'll do summary, GSS, $sign. Let's just do age again in this case. And like for a numeric variable like age, we run summary, it gives us the 5-number summary plus the mean. So the 5-number summary is the minimum, the maximum, the 25th percentile, the 75th percentile, the median, and the mean. All right, so it gives us a lot of information about a distribution. And we'll talk more about this in week 4 of the class. But we can see, that the sample ranges, they're all adults, goes low as 18, all the way up to 89. So classes of variables. So variables can have different classes depending on the type of information that's in them. These roughly correspond to the level of measurement, so like nominal, ordinal, interval ratio. So for instance, the class of GSS $sign age is it reports numeric. So a numeric variable is one that's either interval or ratio. It contains quantitative information. We can do arithmetic, with these variables. We can calculate their mean. We can add stuff to them. We can divide them by stuff. So like you can do all those things with a numeric variable, okay? Numeric, so that's one type. Now, another type of variable, this one is not actually included in these data, so I'll make one up right here, is a character. So a character variable, you'll sometimes hear me call variables vectors. That's a matrix algebra term for a column. But a character vector is one that contains string information. It contains just text that has no categorical or numeric meaning to it. It's literally just words. So for instance, I could make just some standalone character vector. I could call this name, say name equals, now C is a function that stands for concatenate, and that means put all these things together. So let me just collapse this up here so you can see this when it shows up. So I might make a character string of names, just say, Jason, my friend Mike, my wife Bex, my sons, Cameron and Caleb. And so I could note that there's a comma in between each of these, and these all have text. They have quotes around them. They're all green, means that they're text. And then I have a closed parenthesis around my concatenate. If I run that, notice that I now have this just random variable here called name, and it is a CHR or a character vector, that contains the elements Jason, Mike, Bex, Cameron. If I just write name down here and ask it to print it, it reports all those out. Now note, you cannot do math, with character things. So I cannot say, give me the mean of this object called name. Warning, well, it gives us an NA, which is what R is missing in R, or kind of a nonsensical numeric value. Argument is not numeric or logical, cannot calculate the mean. Oh, well, what if I did name plus 10? What are you trying to do? Like, this is what R is telling you. Like, stop it, stop it. So character variables, you cannot work with them like numeric variables. So that's another type. Now you might think, so for instance, let's make another character variable here. So I'll make one that's called political equals C. And then let's say that this is like how people identify their political parties. It might be, say ind, for Dem, Rep. Okay, so for like 1 independent, 2 Democrats, 2 Republicans, for instance. I could run this and it pops up with this character vector here. Now, this kind of variable is what we would typically consider to be like a nominal categorical variable, though, where it's got category information about respondents. Now, in R, we don't want to encode those variables as characters. Most often, those variables are coded, and we'll see some of them here, as what are called factor variables. So a factor is one that is basically, it has categories, but there are specific categories that are allowed, in that particular variable. So here, like if I were to, let's just take this same thing. I'm going to copy this down here. Okay. So I just copied that. I'm going to write, political F for like political factor equals factor, and then paste in, what I had written here. So factor C. Let me just and run this. So it returns factor with 3 levels: Democratic, Independent, Republican. So when you factor something, it says, what are the unique values here? And it assumes that those are like unique categories, for that variable here. So categorical variables that we work with, we want them to be factors. And luckily, that is how the read SAV function, when you do this, is how it works with categorical data. So factor variables are categorical data. Now we have some factor variables in our GSS data set. So for instance, there is in our GSS data, say table, GSS $, there's a lot of categorical ones here. We'll do courts harsh. So what this is this is a question where people were asked, hey, how do you think the local courts deal with crime? Are they too harsh? Are they about right? Or are they not harsh enough? And then people give their response. Now, this is technically an ordinal variable. Basically the higher the values go, the more punitive, the person feels, about crime, the less satisfied they are with how the courts are dealing with crime. But these are separate categories. This is a factor variable that has these allowable categories to it. Now, you cannot do, if I do a mean, GSS courts harsh, says I cannot do math with a categorical variable, and that's fine. Okay, so like we need to do certain things, like I mentioned in the last class, the level of measurement unlocks certain things that you can do with a variable. If it's categorical, we can count it, and we can look at their frequencies. If it is numeric, we can also count it. We can look at the unique values, but we can also do math with it. So the major types of variables that we'll work with in this class are numeric and categorical, or numeric and factor, for being the quantitative and the categorical. There's one other type that is worth mentioning here, and those are logical variables. So logical variables are the equivalent of binary variables, like 0, 1 variables in R. So notice here, let's say, so what I'm going to do is I'm actually going to make a new variable, in my data. So GSS $, and I'm going to specify a variable name that doesn't exist yet. So I'm going to call this age over 50. like let's say I want to identify respondents in the data who are over the age of 50. I'll say age over 50 equals, GSS $age greater than 50. Now, let's check out kind of how this works. So first, this here is called, this is a logical operator. And when I say, so take this variable, and then this greater than symbol is saying, evaluate, each of its entries and tell me whether or not this is true. Okay, so I run this, and then we'll do table with GSS $age over 50. Run that. And also note, when I ran this, it made a new variable. I now have 24 variables up here. Okay. It gives me values of false and true. So what this tells me is that there are 734 respondents where this is not true, so they must be less than 50, and there are 587 who are over 50. Now, you'll notice here, if I write true in all caps, it turns blue. So R knows that true and false are special values that mean 1 and 0. All right, so like true is equal to 1, false is equal to 0. What I could also do here is, if I said, we can convert like one class to another. So if I said, so GSS $, oh boy, all caps, that's not good. So GSS $age over 50, and then put an N at the end of it for numeric. And I said, equals GSS, $ age over 50. There's that pipe again. This means take this and then do this as dot numeric. What this means is take the variable GSS age over 50, %, greater than symbol, %. So then convert it to numeric. Run that. I now have a 25th variable, in my data. And if I do table GSS age over 50N and run that, again, I have 734 and 587, but they are zeros and ones. Now, R thinks of these two types of variables as being equivalent. So like we can take the mean, of a logical variable. We can take the mean of a binary variable. So yeah, we can do those things. Now, we can also, one more logical here is we could make variables that, like binary variables in another way, where let's say that we have our political ideology variable. Let's just take a look here. So table GSS $ symbolic ideology. Run this. It has these values. Now I copied this off of a specific study that was really interested in examining conservatism. So that's why it collapses liberal into just one category here and splits out conservative. So that's just the reason for this. But let's say that I wanted to make a variable that just identifies whether or not the respondent is liberal. Okay, so what I could do is say, so GSS $, we'll call this liberal, equals, so GSS $ symbolic ideology equals. So that means is equal to, and then in quotes, what is the actual value of this variable? So down here it is liberal, all lowercase. So I'll copy that and put it in. And then run this. Now I've got 26 variables up here. And so, if I was to, you can click on this now, and any new variable you make will always go over the end. I can scroll over and see I've got these trues and falses. So these people must be liberal. These people must be something different, moderates, or some level of conservative. So that's another way we can make binary variables with one of these logical operators here. This is something we'll do in varying capacities as we go. They're logical operators. We'll cover this more next week. They can do lots of different things. Okay. So we're going to take a little break from R for a minute here. We're going to go back to our slides and start talking about, okay, so how do we want to display data? What's meaningful stuff to display, about, in univariate and bivariate senses, and then how do we do that in R? So this will be a placeholder for right now. So I'm going to save my script after all the work that we did. And again, if I wanted to come back and rerun all this, I could just reopen my script, run it all down to the bottom. Okay, so let's go back to our slides. Okay, so let's say that we want to summarize the contents of a variable, right? So there are two ways we can do this. We do a tabular display where we indicate the results in a table and then have numbers to represent properties, or we could do it graphically. Okay, so we'll talk about both of these here today. So in a tabular display, what we were essentially doing is creating kind of a summary matrix, to define the contents of a variable, where we would have specific statistics that we're calculating. So these could be like, depending on the level of measurement, as we'll see, if it's a categorical variable, maybe we would have the frequency, the percentage and the cumulative percentage, and then we'd have the different categories of that variable. If this could be a numeric variable, and we might have the mean, the standard deviation, the range, for instance, but we display that information as a summary in a table. Graphically, we're going to do that visually, and this can be useful in varying capacities. Depending on the context, if you're giving a presentation, I'm always going to value graphics over tables. If I'm writing in a report for practitioners, I'm always going to value graphics over tables. But if I'm writing in a scientific manuscript, usually you want to do a little bit of a mix, but tables are highly prioritized there because of how specific they can be. So we'll talk about univariate and bivariate displays. So like any univariate display is we're just displaying the contents of one variable at a time. So there might be multiple variables in that display, but their distributions are only for each of those variables considered alone. And so what we might have is like looking at a data set of non-fatal injuries. We might have what's the gender of all the victims here. We would see that. A bivariate display will have the joint distribution of two variables at the same time. So it might be, depending on the level of injury, here's the male and female breakdown, or in this case, the support for a president, support or do not support, or candidate versus this candidate by political party. And those things are broken down jointly as opposed to done one at a time. There are also, we could do more complicated multivariate displays of information. These can be useful depending on the context, but often univariate and bivariate are going to get us most of the way to where we need to go. So what we'll talk about here is, covering, univariate tabular displays for categorical and numeric variables, univariate graphical displays for categorical and numeric variables, and then bivariate tabular displays, et cetera, et cetera. So we're going to kind of go through this as a taxonomy, for our discussion here. So first, univariate tabular displays for categorical data. So when we have categorical variables, so whether these are nominal or ordinal that we are presenting to others, if we're going to present those results in a table, a frequency table is a pretty common option here. And frequency tables can take on a few different shapes, but this is the one that you'll most commonly see in this class. So here we have a variable from a similar data set, but with different n, that's looking at support for the death penalty. Okay, so a few things to note here. The frequency is simply the count of the unique values of that categorical variable. So any categorical variable, like we saw in R, is going to be a factor. And if we do a table on that, it will report out how many times does this specific value show up in these data. Now, if the data are complete, then the frequencies will add up to the analysis sample size here. That's the total number of units that are summarized by that. So we'll represent that with the capital letter N. Now, when we're presenting information, we often want to avoid redundancy. And so here, it's probably a little bit much to have the total N in both the title and in a total row down here. Usually we want to avoid redundancy, but you do at some point want to communicate what is the sample size that's being represented here. Okay. Now, if I give you the total frequency, if I just say that's right, so of this sample, 596 favor the death penalty, 292 oppose it. That can be useful to the extent that you have as a reference point the actual analysis sample size, but it doesn't immediately communicate anything about the relative rate here. Like, I don't know, is that high? Like out of the total sample, is that high? Is that low in terms of support? I'm not really sure. So what we can do is we can represent that information using a proportion, or a percentage. Now, these two things are very similar to one another. It's just we're rescaling one of them. So basically what we're doing is we're taking the frequency, and dividing it by the total sample size. And so if I take 596, divide by 888, I would get 0.671. So proportions range between 0 and 1. If you take the proportions for all the different categories of a variable, they will sum to 1. But here, this tells me that basically 67%, of the values of this variable fall into this category, while 33% fall into this other one. Right. So now I have more information on the relative here. Now, proportions are useful for statistical modeling later. So like if you take the mean of a binary variable, it will give you a proportion. But usually if we're going to present this information in a paper or report to others, they're looking for a percent, which is where, well, let's say out of every 100 units, how many will have this value? And that's just the proportion times 100. All right, so take the proportion, multiply it by 100, you will get the percentage. But it is very easy, just do a little bit of math in your head, that you can convert a proportion into a percentage and understand how they're related to one another. Okay, so a few things on presentation style. So first, for any given table that you create, you should give it an informative title so people understand what's being presented here. And so including the sample size in the title is a pretty common norm, in applied, criminological research. So I'd recommend getting in the practice of doing that. For clean formatting, you should use a consistent number of decimal places. Now, the decimal is going to be the level of precision in those specific statistics that you've calculated. The more the decimals, the more precise the statistic. Honestly, in a case like this, we really don't gain a lot from having 3 decimals as a very high level of precision. Like 2, is usually fine. But whatever you do, you should aim for consistency. So like when you're working with R, you work with any other statistical software, I feel like they often spit out completely arbitrary numbers of decimals. Like you could ask for a proportion, it will give you 10 decimals. It'll give you 5, it'll give you 4, etc. Whatever you're presenting in a table, you should just be consistent, with how you do that. So like, as I'll highlight, here, also when we ask R to produce statistics for us, we don't just then copy and paste that into a document and say, here you go. What we are doing is we are using the software to calculate quantities of interest. And then we are organizing that information into a table, like using Microsoft Word. We are typing in that information by reading it with our eyes over into, and then typing it in, to this table. So there you can do some rounding, or we could ask R to round for us, but we are typing that in, here. So just aim for consistency. So if we have an ordinal variable, a useful proportion method measure, or you could also do a percentage here as well, is the cumulative proportion. Now, this is from category to category, how much of the total sample has been represented by all the categories up to this point. So for instance, looking here, let's say we have this variable is looking political ideology. This ranges from extremely liberal to extremely conservative. Now it's ordinal. So we could say, only 4.4% of the sample identifies as extremely liberal, 13.4% identify as liberal, and 12.8% identify as slightly liberal. If we add up those cumulatives, this tells me that 30.6% of the sample is some level of liberal here. And by the time we get to liberals and moderates, we have covered 66, 2/3 of the sample. So this is a pretty equitable split in terms of liberal, moderate, conservative in this particular sample here. But the cumulative numbers are only useful if there is some ordering to the variable. Plenty of software like SPSS and JASP is another one. They will report out the cumulative percentage by default, even for categorical variables that have no ordering or only have 2 values, and it is completely useless in those circumstances. That's why, it is your responsibility as the researcher to, you run certain functions, you calculate certain statistics, it gives you some information that's useful, and sometimes it gives you information that's not. You need to know when that's useful, when it isn't, and you present what is actually useful out of that to the reader. You don't just spit out quantitative, software output and say, oh, no, this is what the software said. It gave me percent, valid percent, cumulative percent. They're all the same. I don't really know what they mean, but here you go. Like, you don't want to do that. That's when you are doing a bad job. But again, useful for ordinal variables that have 3 or more categories. So another way of representing kind of, so let's say that we've got some numeric data here, is we could represent things as a particular rate per some normalizing constant here. So let's say that we have data where we've got for several states, we've got the number of law enforcement officers, we've got the total state population. We could look at this and we could say, all right, so which state has the largest law enforcement presence, like the biggest police strength, for instance. If you just looked at these raw numbers right here, you'd be led to believe, oh yeah, Vermont is bottom of the barrel in terms of their, the strength of their police force. Massachusetts is far and away, running away with the show in terms of, for these New England states, how strong are their police forces in terms of numbers. But one of the things is that those numbers don't account for the underlying denominator here, which is what's the total exposure or the total opportunity for those counts to accrue. So what we could do is we could take sort of the number out of which this other number could grow, and we could normalize this by that to convert it into a rate. So a rate is simply the frequency divided by the population. And when you do that, the rate is usually some number that is ludicrously small, some extremely small number. So what we would do is we would turn that into something we could actually communicate or statistically model by then multiplying it by some constant. So like a per capita rate is per 100,000. Here I just did by 10,000. And so once we do this, we'd say, for every 10,000, whatever's in the denominator, for every 10,000 population, here's how many police officers there are. And now when we look at this, we still, can see that Massachusetts is on top in terms of its law enforcement strength, but nowhere near as strong as we thought it was based on just these raw numbers. And in fact, Vermont is not really that far behind other states. It's actually got a larger, relative police size than Maine, based on the number of population for the state. So rates can be useful when you have that underlying population exposure that varies from unit to unit. Okay. Let's look at how to do these particular things in R, just to be clear. Okay, so first, see something I need to update in my slides here. Okay, so first of all, to get the, we've already seen, so to get a frequency table, so these are the tools we need for frequency tables. We can use the table function to get frequencies. Let's do table GSS $, support death penalty, right? And so we get the different values, of that variable. We get no's, we get yeses, and we can see this 458 and 863. Now, if you want to know, okay, well, what's my sample size here? Like, how many units are in these data? So first, there is this up here. We can see that it's 1321 rows in our data. We could also just take this, we copy that, and do sum table, so function within a function, and it gives us what's 458 plus 863. You could always just add them together. So 458 plus 863, 1321. So we could do that to get the frequency and the n. Now, what about the proportions and the percentages? Okay. So here, that would be, so there's a few different things that we could do to do this. Is first, we could do, I wouldn't necessarily recommend this, but so table, GSS $ support death penalty divided by n row, so that's how many rows are in my data set. So notice here, this is a bit of the programming aspect to this. If I just highlight this part and run it, note that it returns 1321. How many rows, so n row, are in your data set? So what this is really saying is take these numbers and divide them by 1321. Now let's say that my data set changes size for some reason. I get more data up here somewhere in my code. I remove cases. Well, no matter what I did, this will always give me that, the number, as opposed to me writing in 1321. That's only accurate if the actual data size is 1321. So I'd always encourage you to think about things like this. Okay, so this gives us proportions. Okay, we could always take this, put that in parentheses for order of operations times 100. Okay, and so it gives us, that's the percentage. Now there's another way to do this too. This is what I would recommend doing. Is there's a specific function for calculating proportions and percentages. So that's prop table, so for proportion table. Now what the prop table function wants is it wants, as its argument, it wants a table. So like if I give it this table, so prop table, GSS $ support death penalty, and run that, it gives me that proportion. I can do that times 100, it gives me the percent, right? So this is how you can calculate that information. So here, like if I wanted to essentially recreate the statistics I needed for that previous death penalty table, I would do this. So like, we would need, so table, GSS $ support death penalty, for the frequency, and then prop table, and then copy that, paste it in, times 100 for the percent. Run that, and those are the statistics that we would plug into our table over in Word. And then if we wanted to, we could jump down to the next variable, and start doing that one. Okay. Right, if we want cumulative proportions, then we need to incorporate the function cum sum. So let's do so here, let's just take a look. We do table GSS $ symbolic ideology. We get our frequencies, for our different political ideology categories. So again, let's copy this because we're going to use this for a bit more. We could do, prop table, and then paste that in, and there's our proportions. So now, if we were to take this, we could do cum sum, open parenthesis. Let's copy that whole thing. So a cumulative sum of our prop table. What this will do is we'll take each corresponding number and add them up and then report back the sum as it goes. So these are all of our cumulative sums by row here. As you can see, like, 0.302 plus 0.36 is going to give you 0.663. So that's how we would get the cumulative proportions here. And again, if we multiply that by 100, it gives us the cumulative percentages all the way up to 100. So you'll see, in the exercise, for this week, what you need to do is calculate frequencies and percentages for specific variables on data set and put them into a table. And I guess I should be abundantly clear what I mean by that, just so people are clear on this. I mean, I don't want to go super long with this lecture here, but I'm gonna open up Microsoft Word here. I think I'm gonna open up Word. Sometimes computers working a little hard. Okay. So get this a little bit smaller. Okay, that's better. So it was nice enough to open twice. So here, this is getting a little busy. So I'm going to do Control or Command L to clear out my console. So here, let's say that what my task is so like exercise 1, make table. Okay. So what we're going to do is, I think the instructions are going to be something like, give me the variables, give me a frequency, give me a percentage. So let's say that we want to do that for 2 different variables, right? So up here, let's actually do this I'll do this right here. And it's going to do this for support death penalty. And let me just work smartly. I'll copy this. And I'll just swap out support death penalty with another variable. If they support, if believing people should have a permit to buy a firearm. Okay, do that, paste that in here. So now I've got these 2 variables, right? So what we want to do is let's make a table. So up here in Word, we go to Insert, Table. So I need one, what's the shape here? So I don't know how many rows I need yet, but start with 4. I know I need 1 column for the variable names. I need 1 column for the frequencies. I need 1 column for the percentages. All right, so we'll start with this as our table shape. If I want to make this into a title, I'll do, merge cells, table 1, statistics for general social survey, n equals, and again, if I want the sample size, say n row GSS, n, it gives me 1321. Okay, so now that's going to be 1,321. Okay, so then I've got variable, frequency, which has an R in it, percentage. Okay, so now I know I'm gonna need more space than this, so I'm just gonna highlight here, and up here in the table layout, I'm gonna click insert below, and I'll just start with this. So the first one I'll do is support for death penalty, right? And I know it's got 2 values. It's got values of, so let's do 1, 2, 3, no, 1, 2, 3, yes. So again, this type of heading here, this is called stub heading, where this tells me, okay, so I've got this variable, these are values of that variable, okay? And so here, let's calculate those statistics. So there's our frequency, there's our percentage. Let's go back here to Word. So I know that in that no category, they're 458, boy, 458, 863. I know the percentages are 34 point, we'll do 1 decimal, so 34.7, 65.3. That adds up to 100. Looks good. Okay, so now we could go on to the next variable. It looks like I'm going to need one more row here. So we'll insert below. Let's check out this one. So support for firearm permits. Okay, looks a little bit different here. So we'll do support for firearm permits. 1, 2, 3, no. 1, 2, 3, yes. We could do so 349, 972. And again, like I'm reading these numbers over here in. Now, R is a little bit better about this than other software. Where if this was SPSS, it would spit out a ton of stuff at you, including a bunch of garbage that we don't need. Okay, R is very explicit in terms of what you ask it for, it will report back to you. So we're only really getting what we want. And then in the percentages, so 26.4, 73.6. And then from here, and notice like what I've done is I don't have like table 1, support for death penalty, frequency percentage. Table 2, support for firearm permits, frequency percentage. This is all the same sample, different variables describing that one sample. I can put these all into one table. So if I ask you for a single table that does something, this is what I'm talking about. Is I want a single table where you're displaying univariate statistics for multiple variables here. So now we can customize this, however we like. So I might bold some of my headings here, bold my variable names. I might left align these columns. I might remove the border grid, just add like a bottom border. Okay, like that. The spacing's a little off, but this is much sleeker than, oh, sure, professor. I'm gonna paste it. Oh, come on. Sure, professor, here you go. Here's your statistics. Don't do this. Like that's bad. So don't do that. This looks much better. So that's what I mean. Okay. All right, save this. So we've done those things. Okay. Let's talk about graphical displays. Okay. So when do we want to consider using graphics? So like so again, we've presented stuff in a table, and tabular presentations are useful because of how precise they are, and they can be good in a variety of different contexts. But data visualization, using figures and graphics for describing information, are useful for both communicating with audiences and understanding more about what's happening with your data that you might get obscured when you use summary statistics, descriptive statistics in a table. So for instance, right here is a table that is displaying the results of a regression analysis, which we'll talk about later in the semester. It's looking at what is the effect of gun ownership within states, or the association of gun ownership within states on firearm related deaths. And so like, because I know how to read this table, like this tells me that basically when gun ownership increases, the firearm death rate also increases. Okay, so I have that information from this table, but if I'm just putting this in a presentation, for instance, to talk to an audience, this is not super intuitive, to present to some people. So like what we might consider is encoding this information in terms of positions, in terms of colors, in order to communicate this. So like this is an equivalent representation of that table as a figure. This is a regression line that shows the relationship between as the percentage of the households owning firearms in the state goes up, so does the rate of firearm deaths per capita. I can see that quite clearly, here in this picture. So there are reasons why we might consider in some circumstances we would want to do this, and other circumstances we would want to do this. Now, importantly, there are diagnostic reasons for visually inspecting your data as well. So like this is a famous example in regression analysis called Anscombe's quartet, where, so again, going back to this table, if I, let's say that I had different data sets, that had different properties. If I were to, run the same regression analysis on them, I would get, 4 tables that all look exactly the same. They have all the exact same intercepts. They have the exact same regression coefficients. But if I look at the underlying data, so look at these lines. These regression lines are all exactly the same. The intercept is exactly the same. The slope is exactly the same. But when you look at the underlying data, it's very clear that these data sets are very different from one another. And this is where the tabular information can obscure, certain things. So in this top one, this is clearly the instance where you would want to use a regression analysis. And this describing this association with a straight line makes sense. In these other cases, it is far from the truth. So we can use data visualization as a diagnostic technique for how useful certain statistics would be. This is another example written by Kieran Healy, a sociologist at Duke University, who's well known for his work with R. And again, all these statistics, all these graphics are produced with R, by the way. These are all the same things. They're all the exact same regression line, the exact same intercept, but obviously super different data situations. So it's just highlighting that we should visually inspect our data if we want to understand more about what's happening underneath the hood and how appropriate certain techniques will be. Now, it also makes it much easier to communicate with audiences. So like, as an example, like this is something you might see where like, okay, so this is a paper that I wrote. This table got formatted really, really bad. It's probably the worst table I've ever made, just in terms of how big this was. But I had to fit a ton of information, into this table. This was looking at the effect of a specific police intervention on crime in the city of Flint, Michigan. And this is fine for a tabular presentation in this scientific manuscript because I need to present really precise information about the effectiveness of the program and the statistical uncertainty around those effects. But what a lot of people do is then like, okay, well, let's say I'm going to present this at a conference. They'll say, oh, I'll just take the table that I put in my manuscript. And you will hear people say, okay, so here it is on my PowerPoint slide. So I know none of you can read this, but, and then they'll kind of laugh and then they'll point at things maybe with a laser pointer. But seriously, if you are saying, I know none of you can read this, why are you putting it in a presentation? Why are you presenting it to others in that way? That's stupid. So that's where we would think about, are there graphical possibilities for communicating these results? So like, this is not that exact same analysis, but this is a different multiple regression model where I've got, instead of a table of all of these different regression coefficients and their statistical uncertainties, I can present it visually, and say like, okay, well, here's all these different variables. Here's the size of their effects, and here's the statistical uncertainty. And it's much easier for people to see that, okay, well, if this is no effect at all, I can see the variables that have the largest effect, both positive and negative, which ones have uncertainty that crosses 0. So like these are things that we will learn how to do, how to present these things graphically. But this is where we would choose, like, I'm not going to present this as in a table, and say, no, you could read this. Here's a graphic you can read. How about that? Now, this doesn't mean that any graphic is going to do the trick. Some graphics are really bad, for a number of reasons. So like, looking at this one right here, what you have to understand is that there needs to be what we'll call aesthetic mapping with any graphic, meaning that aspects of the graph, like the types of geometries that are presented. So here there are bars, the heights of those bars, the colors, of those things, these communicate information. Now, in this case, you can ask yourself, might be a good place to kind of pause and ask yourself a few questions here, see if you can evaluate here is, so what is communicated in this graph, right? So like we're looking at life expectancy across different continents. So first of all, what is the purpose of color? in this graph? Does color have a unique purpose in this graph? Consider it. No, it doesn't. Like what we have is, okay, I can already see that there are separate countries being encoded here. They all have their own bars. Even if all these bars were black or purple or whatever, they were all the same color, I would know that this one's Africa, this one's Americas, this one's Asia. Okay, so color does not display unique information. There's no reason for this to have different colors. Let me ask you this. Why is this graph in 3D? Like, why are there 3 dimensions? There's one variable that's being presented here. Well, I mean, 2. There's continent and then there's life expectancy, but what is the 3rd dimension? There isn't one. So does having this in 3D, does that represent data in any way? It does not. Why is this in 3D? It only, like, can you actually tell me what the life expectancy is in Africa, looking at this graph? I mean, if you can, then you're smarter than me, because I sure as hell can't. Like here, like this could be all the way over here at like, close to 80 something. Like it's why is there a shadow? It doesn't make any sense. Terrible graph. So the graphs that we'll make will look more boring than this, but they will be practical and readable because every color, every fill, every shape will have a reason for being there. And that's how you communicate with audiences. Okay. Now, there are other ones where, like, you look at this and we could see this graph and like, okay, so this is pretty old at this point. This is looking at political expenditures and different campaigns. And we could tell that it's going up. It's a little hard to tell exactly what some of these are at, in terms of their levels, but this display is very memorable, like in terms of communicating a message. So like, this is good. I think this was in the New York Times, but this would be, I wouldn't be caught dead, putting this in a scientific manuscript because we want to be precise with ours. But again, like this isn't necessarily in bad taste. This is just it's appropriate for the context and communicating with an audience. I'm sure it gets the message across well. And I mean, if we were still spending $300 million on House and Senate campaigns, I think there are probably individual campaigns that are spending far more than this. Unbelievable. So what we don't want to do is, we don't want to cherry pick data. We don't want to represent data that can mislead audiences. An important thing to recognize is that there's no graphic that if your data are bad, like if it's a bad measurement, it's not validly communicating information about this specific, phenomenon that you're looking at, there's no graphic that's going to save you. All right. And so you can end up, really misleading people, if you are presenting things, in certain ways. So like, take a look at this one right here. So this, I think this was also in this was in the New York Times. When you look at this, it was under the headline, "Is Democracy Dying?" And what we have here is basically the cohort of birth of people in a given survey. So like people born in the 1930s, people born in the 1980s. And then we have, it says, the percentage of people who say it's essential to live in a democracy. And so you would look at this, you might say, okay, so people back in the 1930s, people born in the 1930s today, so people who are in, their 80s, for instance, like my grandmother, they would, apparently far more of them think it's essential to live in democracy than these totalitarian loving millennials, born in the 80s, is what you would probably conclude from this graph. However, the underlying data, the question that people were asked was, how important is it to live in a democracy? And they could answer anywhere from 1 to 10. So it's technically an ordinal variable, but it has these 10 values where 10 is the value essential. So what this is this is the proportion of people who answered 10 in each of these different categories. That's a little misleading because this is ignoring all of these other data values. So what if we were to switch this out with something like, let's say, the average for each of those? And so now what we have is what's the average response, as opposed to just who said 10, instead of what's the average response. And yeah, we do see a bit of that decline, right? But it is nowhere near as significant. People still think it is pretty important on average to live in a democracy, just not as much as people born in the 1930s. So again, you can obscure, information here. We will try to focus on, how do you present the most information, that's useful in the graph, and also like, well, you could present it in this way, but you might end up misleading an audience for, a variety of reasons. So we'll think through some of those things. It's also important to recognize that people have, human brains that process information in a variety of ways. The human brain is not perfect, right? So like, there are things that can screw with how the human brain perceives information. So, in this case, if you put stuff in 3 dimensions, especially if it's just one-dimensional data. So again, this is one variable being represented as frequencies. The human brain has a hard time looking at this accurately. And in fact, sometimes the software is actively working against you, where notice here that D has a value of 4. Does that look to you like it even touches the line for 4? No, but it's part of the perception that it's flipped. It's kind of like turned, again, why is it in 3 dimensions? There is no 3rd dimension, so don't do that. This type of graph too, this is called a stacked bar chart. This would also have, some issues where, let's say that you wanted to determine, is the relative representation of whatever C is here, is that increasing or decreasing over time? It's a little hard to put it together because of how the bars are moving in this case. So again, the human brain has trouble kind of putting some of this information together. Now, there has been some systematic research on this, is where what researchers have found is like, you try to ask people, okay, like, hey, what's bigger? Like this bar or this bar, this square or this square? Depending on how you organize it, people can be systematically closer or farther away from the truth. So it's a way of measuring how bad their perceptions are. And so what this really highlights is that there are specific graphs that are easier for people to interpret. Now, again, those are going to be a little bit more boring to work with. It would be things like these basically error bar point charts. This would be called a point range in R. They're more boring than having a gigantic monster eating your campaign expenditures or very colorful 3 dimensions, but they will be workable, right? So what can we do? How can we present this information? But note that too, these are some fun examples. Even the pros screw it up sometimes. Like these are graphs that are in actual scientific manuscripts. So I mean, I've made graphs that I'm probably not proud of as I look back on it. Not as bad as these though. Like, okay, so first of all, pie charts are bad in general because people, if they aren't labeled, people have a hard time figuring out which slice, is bigger than the other. But also, like, why is it in 3 dimensions? Like, what is the purpose of this? What is even happening in this graph over here? Can you tell which one of these groups is which one of these is higher or lower than the other? So really bad. Then you could also ask yourself, hey, is any data represented in this graph right here? It might look like it's blank. The answer is there actually is data. It's all these little points down here. So like, why does the axis go all the way up to 0.05? Shouldn't the axis only go to a maximum of to 0.05 instead of 0.5? Like, what the fuck? So anyways, even the pros screw it up, but we will work our best with starting off a little simply. Okay, so what options do we have at our disposal? So if you have categorical data, so univariate categorical data, the easiest presentation is to do a bar graph. Now, you could also represent this in points. So I could just put a point at the different frequencies right here, but it helps for people to draw their eyes going up to here to understand the relative height. And that tells them, okay, so height is encoding how frequent these different categories are. So we have anywhere from, liberal to extremely conservative. We can see, yeah, there are more moderates than there are liberals. There are fewer extremely conservatives than there are conservatives or slightly conservatives. Now, this generally is going to have the lowest level of reader error. Pie charts are pretty popular, but again, they stink. Part of the reason for this is that unless you label the different ones, so what's bigger here? Like I think it's easy to tell that yellow is bigger than gold, but how much bigger is it than gold? Can you tell? You're better than me looking at this if you can. So unless these are labeled, that's not going to work. Just represented in a bar graph, because that will explicitly tell people how frequent these categories are. Again, it looks boring, but it is what our purpose is to communicate. We are not Russell Crowe and Gladiator, like, are you not entertained? That's not our purpose here. Our purpose is to communicate, not entertain. Yeah, so if we've got continuous distributions here, then here, let me actually see here. Very graphical displays. I think I'll just skip over to the R stuff at the end here for these. Okay, so far we've talked about presenting categorical data. What about presenting continuous or numeric data? So now here, like it's easy to do tabular presentations of summary statistics communicating your different distributions of continuous data. So like I could have a table that has means and standard deviations, and that will tell you information, about a given sample. But if I want to tell you about the entire distribution of a variable, a graphic is the best way to go with that, because I can't make a table, that has all the different values of a variable, let's say, that has 100 different values in it. You imagine a table with 100 rows. We could, group it or bin the values, but again, that does sacrifice information. So like, for instance, let's say that I want to make a frequency table like we've been doing for this variable age. That's okay, what's your age in years? 18, 19, 20, etc. Well, imagine this table that goes down 80 something rows. That is like, okay, well, here's the frequency, and obviously very few people are literally 18. Relatively few people are literally 19. Relatively few people are literally 20, etc. Now, what I could do is if I wanted to present this in a tabular way, I could bin it and group it into things of 18 to 33, 34 to 49. Now this is easier if I want to do a tabular presentation, but again, it does sacrifice information. But again, you don't want to do this. You don't want to make a pie chart, with this either. But the best way for us to display that information graphically would be to use a histogram. And so this is that same distribution. So we can see, these are kind of smartly binned, here, and we can kind of see which values are most frequent. We know that the mean is 47, in our data. It's somewhere right around here. So this is called a histogram, which displays this. Histograms are my favorite for displaying numeric distributions. We'll also use box plots once we start talking about measures of dispersion, because that's explicitly what those calculate. If we have variables that are numeric, but they're measured over time, we can use line graphs for that. So this is one that's looking at monthly violent crimes that are reported to the police in Detroit, Michigan. You can kind of see the seasonal aspects that are happening here. So every peak is the summer, every trough is the winter. But again, we'll cover kind of how to do each of these. Well, let me just see how much I have left here. Okay, we are not that far off from the end. So this is long, but again, you can take it in pieces. So let's actually look at our univariate graphic displays in R before we get into this. So going back to R, make a new section. So R is an awesome interface for statistical graphics. There are lots of different tools for producing graphics. We're going to use one in particular called ggplot. So ggplot was written by one of the main developers at our studio named Hadley Wickham. It is has a little bit of overhead in terms of figuring out how it works, but it is, once you kind of get the hang of it, it is really easy to make very high quality customizable graphics. So first of all, let's try this. So if let's say we wanted to reproduce that graph that had a bar graph that had the different political ideologies in it. So here we've got our data. This is where we're going to go back to those pipes a bit. So I'm going to write, if it insert. So GSS pipe, right? So this means take the GSS data, then, okay, ggplot, okay? So ggplot is our graphics package. It comes with tidyverse. Once you load that in, it'll be available. So what ggplot wants is it wants which variable it needs to tie to some aesthetic mapping. So we're going to write AES for aesthetic. And here, if we're just doing one variable, it's a variable that goes on the x-axis. So we'll call that x. We'll say x equals, and then what's your variable name? Symbolic ideology. And note that once we're doing it like this with the pipes, we don't need to do the GSS $ symbolic ideology. Like it knows that this variable is inside those data. Okay, so we have this. This is what's called the kind of the base of your ggplot. We now need to add a geometry to it, which is, okay, well, how do you want to present this variable? And so here we'll write geom, and then we'll see once you do this, you get a bunch of different, so geom underscore, there's a bunch of different options here. These are how we want to present it. I'll start with geom bar. So we'll take this and I'm just going to, and note, once I hit the pipe here and then hit return or enter, see how that's indented? It knows this is part of the same function, right? So I will hit enter, and look, this is our graph right here. A little bit off from the totals in the other one, but like from this, we can customize it. We can make this professional. We can do a bunch of different things with it. But notice here, so I use the pipe when I'm going from the data to ggplot. Once you're in ggplot, we use plus to add different things to this. So like here's our bar graph for a categorical variable. Then if I wanted to do a histogram, for a numeric variable, okay, well, I'll do the same thing, GSS, %, greater than symbol, %, so pipe. So take GSS, then ggplot, open parenthesis, AES, open parenthesis, x equals, and this time we will do age plus geom histogram, open close parenthesis. Now we'll control enter to run that. We get our histogram of age here. So again, like the geoms, the geometry kind of define how we are, how do you want to show up? What do you want to see here? And there are lots of different things we can customize with this, as we will see later. Okay. So let's talk about bivariate displays. So we'll come back to R, go back to our slides here. Okay, so now we'll start talking about how do we present information from two variables at once. So here, so it's a bivariate display because it is the joint distribution of two variables. So we have two categorical variables, then we can present those in what's called a contingency table. Now, a contingency table is sometimes referred to as a crosstab because that's the name of the function from SPSS. Crosstab is not a thing outside of SPSS. They are called contingency tables everywhere else in the freaking world. So we will call them contingency tables. Now, in these tables, one variable defines the rows, another variable defines the columns. Usually the variable that has the fewer values will go in the columns. And we do that for space reasons. It's easier to fit it onto one page. But right here, so in this example, we have you ever been convicted of a crime? And it has values of yes and no. And then it has how harsh do you think the court should be? So this is, again, from another subset of the GSS data. And so here, like we can see, convicted of crime, yes, no, court's perspective, too harsh, about right, not harsh enough. We see that 56 people who were convicted of a crime thought courts were too harsh, and people who weren't, 179, said that they were too harsh. And we can look here, we might want to draw some conclusion, like what's the association between having a previous criminal conviction and your perspective on the courts. Perhaps I think what we would hypothesize is that if you have previous experience, or if your family has previous experience, you probably have a more grounded perspective, on the criminal justice system in terms of like what happened to you, for instance. We might expect that people who have a previous conviction think that courts are probably too harsh or probably about right, as opposed to being not harsh enough. However, it's really tough to test that here because the different totals across these categories are different. All right, so like it's really hard to compare just those frequencies. So what we need to add are percentages to each of these. Now, these should not be the raw percentages. Like these should not be 56 divided by 1576 and 179 divided by 1576. What's most useful is to have these be some marginal percentage, which is either a percentage that's based on the row or the column total. So right here, these percentages are based on the column total, where these say, of those, of the 192 people who were convicted of a crime, here's the percentage who said courts are too harsh, about right, not harsh enough. As we see these percentages. Of those who said that they were not convicted of a crime, here's those breakdowns. Now we can compare across these categories more easily. Now, these can be easily calculated in R. I will show you how to do that. And it is also up to you which percentage is more useful. Is it the column percentage or the row percentage? It depends on what you're attempting to accomplish. In this specific example, I use column percentages, but again, whatever you use, you should just communicate that. So in the table footnote, I said percentages reflect them of column totals. Okay. So like here's another example, some contingency tables, that I used in my own research that we're looking at. Again, this is that effect of higher education on police behavior in terms of searches, in terms of force. And so, here's some contingency tables in action. We can see that with these percentages that, more force is being used in those who have just a high school or less for education, and pretty equivalent amounts, but less so, for some college or a four-year degree. So it doesn't look like there's a difference between these two, but we see the difference here. Okay, let's jump back to R for a minute. So how do we make our contingency tables and work with them? So we already kind of have the tools for doing this. So if we do, we're going to use the table function to get our joint frequencies. So if we do table, and what we're going to do this time is the first variable that goes in is going to be what shows up in the rows. The second variable is what shows up in the columns. So let's say that we're going to do, so GSS, let's do the symbolic ideology in the rows, so the political ideology, and then GSS $, so support death penalty in the columns. So notice I separated these by a comma. All right, so it's the row and then the column. I run this and I get my joint frequencies. All right, so now if I want to make my contingency table, these are the frequency numbers that I would plug in. Now again, we could look at this and say, oh, what are the differences here? What would we conclude about the association between political ideology and support for death penalty? Well, it's hard to do because of the difference in the sizes between these different categories. So we need our proportions. So I'm going to highlight that because we're going to go back to our prop table function. So prop table, and then drop our table in. Now, note here, so I'm going to start off, I'm going to multiply this one by 100. So we're automatically looking at percentages. But notice here, just by default, what this is doing is it's taking each of these cells and dividing it by 1321, which is not what we want. We want either a percentage based on the row margin or the column margin. So to do that, after our table here, so we input, so prop table, the table argument, now we need to give it something else. So if you give it the number 1, all right, so this is the margin argument. So margin 1 is the row percentage. So this is of those who are liberal. This is how many oppose the death penalty, and this is how many support it. Of those who are moderate, this is how many oppose it, this is how many support it. We can see like basically all the moderate and conservatives are pretty consistent. It's the liberals who are on the other side. Even they like themselves some death penalty a bit. If we were to switch that up, so this is, let me just be clear here, I'll say this is row percents. Copy this. Column percents. So I'm going to change this to 2. Now this says of those who do not support the death penalty, this is how many are liberal, moderate, conservative, etc. Of those who do support the death penalty, this is how many are liberal, moderate, conservative, etc. And so this still provides some comparison. I think probably the row percentages are a little bit easier to interpret here in this specific case. And then, for your contingency table, you also want to include, like if I go back to this here, like typically you want to have the column total, the row total included as well. So again, if you want all of that information in one place, we would have, so this is the variable that's going in the rows. This is the variable that's going in the columns. Okay, so like this is giving us all the information that we need to compute that contingency table. All right, just about finished here. So graphically, how do we present that information? So one way to do this would be to use clustered bar charts. So here, there are a couple different ways that we can accomplish this. Unfortunately, making a clustered bar chart where, so here we can see we've got, this is a variable that used to be in these data, the skeptical of science as an institution, separated by gender. We have our 2 bars separated by the different categories, and we can compare across them. I basically conclude here that there's a bigger gender gap, in skepticism and science, among those who say yes, as opposed to those who say no, right? So to create something like this in R, we need to do a little bit of work to get this thing to pop out correctly. So let's take a look here. Yeah. All right. So in order to make that, and no, you don't have to do this for exercise 1. This is just something you can learn how to do. Do bivariate tabular display. Okay. So actually, the first thing that we want to do is we actually want to make a separate data set that is just the counts of those different categories that we want to present. So what I'm going to do is I'm going to create this, create an object called GB, stands for group bar. I'm going to say GB equals GSS, and then a pipe. So what this is saying is start with the GSS data set. Then, so group by, it says, so group all the data by the categories of the following variables. And we will do, let's do support for the death penalty. And we will do gender, which is encoded as the variable male here, which has values of male and female. Okay, so we're saying group by those things, another pipe. So take these data, group it by these things, then summarize, and I'll make a new variable called frequency equals, and that's just n open close parenthesis. And so what this says is take our data and then give me a variable called frequency, which is simply how many cases fall within these groups. Okay, so let's check that out. So what does that look like? So I'll actually just type GB right here. And so this shows us that, so of those support the death penalty, of those no, here's how many females, here's how many males. Of those yes, here's how many females, here's how many males. So this we can turn into a group bar chart. So now what I would do is GB height ggplot, and we will do, so AES, so X equals the support for the death penalty on the x-axis. We will do Y equals the frequency. So the frequency of what we see there goes on the y-axis. And then we're going to alter the color fill of each of the bars. And so we'll say fill equals male. So we're going to change the fill based on the values of that variable. Okay, this will be pretty cool. So we'll do plus geom bar. Now, here we need to do a couple things to play around with this to get this to come out right. So first, usually what geom bar does is it says, okay, let me take all the values of the variables that you provided me and I'll count them up. Well, the thing is here in these data, there's only 4 values, right? There's just these different frequencies. If we want it to literally present bars that represent these numbers, we say stat equals identity, which means present what you see. So again, this is something that will come up again when we do regression modeling next semester. But stat identity is basically like present exactly what you see here. And then one more thing that we'll do is we'll do position. Oh, I did not spell that right. Yeah, position equals position underscore dodge. And this means move the bars a little bit. So let's run this and see what we get. Okay, so here's our group bar chart. We can actually see here that this is giving us these different frequencies for each of these categories. It's a little misleading because there are different numbers of people who support the death penalty. So like one thing we could do is, what if we went back up here to our GB here, added a comma, we'll call this PCT, so for percent, equals the frequency divided by, would the sum of frequency work? By the sum of frequency. That would give us a proportion, I think, times 100. Let's see if this works. Actually, I have to move my face screen. No, it just gave us 100. What would we want that to divide by? You know what? Put a pin in that. I'll have to think about that one a little bit. This is fine for right now. But the idea is that if I could calculate the percentages that those are, out of their relative totals, I could present that information instead. But okay, so got that. Okay. Yep. Now let's say that we have 2 numeric variables. We want to present those, again, using bar charts would be a little weird. So we could present this using a scatter plot. This is where we'd have our different variables on the X and Y axis. So we'd have one numeric variable on X, one numeric variable on Y, and then they would present the dots, at their intersection here. And so this would be useful, for presenting the distribution of the joint distribution of 2 numeric variables. Let's see here what I want to say about that in R. Yeah, so I think what I want to highlight instead, because it's going to be a little while before we start doing these points, is I want to talk a little bit about customization here. So like, let's do. So here's this this plot here. This this one, right? So let's say we want to customize this a bit. So what this means is after we've kind of created our plot, I'll do a plus sign, and we can start adding some arguments here, that will augment the visual features of our graph. So like for one thing, we have some defaults here for the labels. So here I'll do labs. That's our labels argument. So labs. So on X, I want that to be, so in quotes, support death penalty for murder. And like you can just run this and see how it updates. Oh, what did I do? There we go. Must have misclicked. So now we can see that this label down here, support death penalty for murder. Okay, that looks better. So we'll add some more here. So comma, y equals, in quotes, so say number of respondents. Okay, run that. Okay, that looks a little bit better. We could add a title. Title equals, in quotes, figure 1, support for death penalty by gender. Okay, we've got that. So the labs argument, augments how we can, these the different the title, the x and the y axes. There are, let's say that, so this here with the gray background, this is the default ggplot background. I mean, I don't know why that's the default. I think it looks kind of crappy. So plus sign, then we'll do so theme. And then there are a bunch of default themes that you could pick from. So like I like theme classic. So here, like I think that looks a little bit classier. If we wanted to augment the colors here, there are lots of different color options in R. So to do that, we have to think about, all right, so what's controlling the color? Here, the color is being controlled by the fill aesthetic. So we would do scale underscore fill and then manual. And here we can give it a different name. So we'll say name equals gender. So that will change this where it says male. And then for the specific colors, we'll say values equals C. And then we could just say like black and gray, for instance, and another plus sign. Okay, and so that's another way that we could do this. Now, colors, you can designate a bunch of ways. They have numbers, they have names. You can look up how to do colors in R, and they'll have lots of different options. But anyways, I've laid out a ton of stuff on the table. I think it's be helpful to stop here, and we will get caught up with this in the next class. It's gonna be a lot, for students to go through. So I don't want to press, but the main idea is that once we get to this next class, if you have any questions, we'll just work through it. By the time we get to the end of class, you will have everything that you need, to do exercise 1. And we will, again, there's not a ton that we need to cover, in class 3. So I will make sure that we are fully caught up by the end. In any case, I'm winded. So thank you so much, for your attentiveness. And I will see you back in person next week.